Hello everyone, I'm Giuseppe Averta and today I will present a paper to grasp or not to grasp, an end-to-end deep learning approach for predicting grasping failures in soft hands. The usage of compliant and soft elements in robotic hands is a formidable tool for endowing them with previously unmatched capabilities. The embodied intelligence mechanically performs the larger part of the grasping and manipulation task, while the physical flexibility enables an effective adaptation with items and environment, overcoming local uncertainties. These hands come with clear advantages in terms of easy to use and robustness, if compared with classical rigid hands. Indeed, during a grasping task, even an approximated estimation of the relative hand-object pose is sufficient to achieve a successful grasp. However, unexpected situations may happen, and the hand may fail while trying to grasp difficult objects. Under a control point of view, the controller should promptly react if the hand fails in grasping the object, so that a recovery routine can be triggered. This makes detecting failures a key topic for the development of an effective control architecture for soft robotic hands. A typical strategy to detect grasp failure is to directly measure contact forces with dedicated sensors. For example, Krug et al. Employed this strategy with rigid hands, while Aggiodani et al. Adopted a similar strategy in the context of articulated soft hands. This is, however, a strategy that is hardly feasible in the generic soft case, especially for what concerns continuum soft hands. A promising alternative to force sensing is to measure other sensor sources, such as video streams as proposed in She et al. Or hand postures as proposed in Della Santina et al., and then infer contact forces through algorithms. Nonetheless, model-based techniques are hard to use in these cases due to the well-known difficulties in formulating reliable models of the hand-object interaction when softness is involved. This paper moves from the following consideration. Since in any case advanced failure prediction involves the use of machine learning strategies, even when force sensors are available, why do not directly learn an end-to-end mapping from the raw sensor to the detection of the failure event? We tackle this challenge exploiting deep learning techniques. The sensing strategy relies on a set of distributed inertial measurement units as a reliable source of contact information in soft hands. First, we propose a deep neural architecture able to distinguish between failed and successful grasps. This serves as a ground truth and a motivation for our second neural architecture, able to reliably predict failure events several seconds before they actually happen. We propose here to use a set of IMUs to acquire information on soft hands movements. A total of 16 IMUs are rigidly fastened to a deformable glove, which can be easily added to any soft hand without spoiling its softness. The first hand is an articulated soft hand, which is called the Pisa IIT SoftHand. It has 19 degrees of freedom and 1 single degree of actuation. The second hand is a continuum soft hand, the RBO hand. Fully made of silicon rubber, it can undergo continuum deformations. From each IMU, we read accelerations and angular velocities expressed along the 3 local axes, and we then have a total of 96 signals. These signals are very full of information, carrying both low frequency and high frequency contents. The first is related to the change in posture of the hand, and the latter to micro impacts and micro slippage events. Measures collected from each sensor are listed in the vector xt, and all the measures are then packed in the matrix X. We analyze failure detection from two strictly connected points of view. First, we tackle the case in which the goal is to classify whether one execution resulted in a successful or a failed grasp. The whole sequence X is considered available as an input to the whole network and is classified between two possible conditions, success or failure. The network is designed combining a convolutional neural network, which acts as a feature extractor, and two fully connected layers, which combine feature describing specific time intervals and/or local events inside the SoftHand itself to achieve global features. Second, we consider a more challenging problem in which the purpose is to detect online slippage events to reliably predict failure events several seconds before they actually happen. Hence, the goal is to predict, at each time t-signed, the success or failure of a grasp, given the current sensor readings x measured in t-signed. In other words, the element in position t-signed of the output is actually only function of the measures collected up to t-signed, and its value is equal to 1 if there is a relative hand object motion in that specific time frame. 0 other ways. The network is realized combining a convolutional neural network, which acts as a spatial feature extractor, and two long short-term memory layers to exploit temporal features. As I said, for the experimental setup, we used two soft robotic hands, the Pisa IIT SoftHand and the RBO Hand, to grasp 6 objects with different shapes and surface roughness. A camera was used to record the whole experimental execution. Accelerations and angular velocities of the fingers were recorded through a custom glove endowed with 16 AMUs. Then, with the goal of acquiring a dataset to be used for training and validation, we carried out a series of experiments in which an expert user maneuvered the soft hands through a handle. We recorded the grasp of 3 different objects: a L-shaped polyhedron, a pyramid, and a cylinder. Each object was presented 2 times, first covered with a rough surface and then with a smooth surface. The idea is to provide a network with examples of prototypical shapes and roughnesses. Each acquisition was repeated 5 times in 2 different experimental conditions: object free to move, resulting in a generation of successful grasps, and object fastened to the surface through a fixed length wire, resulting in a generation of failed grasp. Considering the case of the grasp execution classification problem, we use both successful and failure grasp executions. We then trained and tested the classifier on 3 datasets: one containing data from the Pisa IIT SoftHand, one containing data only from the RBO Hand, and a mixed dataset obtained by merging the first 2. We randomly split the 3 datasets in 80% for training and 20% for testing. Our experiments demonstrated that the classifier is able to detect with an accuracy of 93% in the case of Pisa IIT SoftHand and in 100% of the cases for the RBO dataset, and 95% in the mixed dataset. Considering the grasp execution prediction, we used only failure grasp datasets. This choice has been carried out to avoid to polarize the network towards successful examples. Also in this case, we trained and tested the predictor on 3 datasets, one related to the measure of the Pisa IIT SoftHand, one containing data from the RBO Hand, and the third one which is the mixed dataset. And again, we split the 3 datasets in 80% for training and 20% for testing. In this case, the predictor is able to detect with an accuracy of 85.8% in the case of Pisa IIT signals and 94.2% for the RBO dataset, leading to a 90.46% in the mixed dataset. Furthermore, it is important to remark that the network is also good in not reproducing false positives. Indeed, the accuracy tested in successful examples is 83.3%, despite being trained only on failure examples. We also evaluated the performance of the network in terms of how much time in advance the network is able to predict the failure. The figure on the left shows the difference between the time in which the change of label happens in the ground truth and when it actually is detected by the network. Negative values identify an anticipation. The figure on the right shows how much in advance the network predicts the failure itself. And our approach is able to predict failure events in 100% of the tested cases, with an average anticipation of almost 2 seconds. And now we will show some demos of the system working. Here we have the case in which the RBO hand is grasping a rough, L-shaped object, and the system is online predicting the slippage before it happens. Here instead, we have the RBO hand grasping a smooth L-shaped object and the consequent slippage and failure. Finally, the network is tested on failure prediction with objects of common use different than the one used for training. The reason to do this is to test the ability of the network to generalize to less standardized objects with more complex surfaces characteristics. We tested our approach with rigid objects, like the one on the left, and deformable objects, like the one on the right. Also in this case, our system is able to correctly predict when a failure occurs in 100% of cases, still maintaining a good time anticipation with respect to the failure events itself. And then let's have a look at some examples of the network in use with daily living objects. For example, here we have the RBO hand that is grasping a tennis ball, which is a partially deformable object, and the fixed wire is preventing the grasp to be successful. While here, the same hand is used to grasp another deformable object, a sprinkler, which is heavier than the ball. And finally, here we have the case of a heavy rigid object, which is in this case a stapler. And our solution is able to predict with an average anticipation time of 1.96 seconds the failure of the grasps in all the cases considered in this work with both the tested hands. And of course, we had the chance to test our approach multiple times with multiple objects to statistically validate our results. However, this test cannot be reported here for sake of time, and the interested viewer is referred to the paper attached to this presentation for additional information. Thank you very much for watching this video.